Welcome to the deep dive.
Yeah.
I want you to imagine, just for a second, the sheer scale of the automated systems running our world today.
Right. It's massive.
Yeah, we are talking about literally everything, from the global supply chain to the data centers that are training these, trillion parameter artificial intelligence models, right up to the algorithms trying to discover the fundamental laws of the universe.
It's incredible.
It is. But it also presents a terrifying question, honestly. What happens when the AI systems running our world and discovering our science become these black boxes that even their own creators no longer fully understand?
It's the defining technological paradox of our time, really, because we are building these systems of just unprecedented power, but we're losing our grip on the steering wheel. Relying entirely on statistical guesses and pure correlation, it's starting to fail us. And it's failing at the most critical levels.
And that is exactly our mission for today's deep dive. We are going to explore this massive, critical shift happening right at the absolute cutting edge of artificial intelligence. We're looking at how the most advanced systems out there are finally abandoning that pure correlation, just guessing based on statistical patterns, and they're returning to absolute, uncompromising physical truth.
Which is a huge shift.
Huge. And we've got a really fascinating stack of source material today to help us understand it. First, we are looking at this incredibly dense but groundbreaking academic paper on an AI system called AI Neother.
Really fascinating paper.
Yeah, and we also have some very detailed technical presentations on something called the XR architecture, which stands for extreme reliability.
Yep.
And finally, we're pulling from these complex mathematical frameworks that detail physics-grounded AI.
To really grasp why all of this is so urgent for you to understand, we have to look at the fact that we are hitting two very distinct walls in modern technology. The first is what the sources call the complexity wall. This is the simple realization that human reaction time it cannot govern modern infrastructure anymore. Things are moving way too fast, and they are far too intricate for a human engineer to sit there and monitor manually.
And the second wall, which is just as important, is the interpretability gap. This is really the core problem in scientific AI right now, because an AI can look at this vast ocean of data, right? And it can fit a perfect mathematical curve to it.
But it finds a pattern.
Exactly. It can give you the highly accurate, perfect answer. But it cannot explain why that answer is right. It can't ground its findings in the actual laws of nature.
Which, if you are a scientist trying to understand the universe, or even just an engineer trying to keep a massive data center from catching on fire, that's practically useless.
You can't troubleshoot a black box.
Exactly. You cannot govern a system if you literally do not know why it is making its decisions.
Okay, let's unpack this, starting with the science side of things. Traditional machine learning acts as that black box we just mentioned. You feed it data, and it basically spits out a formula. Now, there have been newer systems designed to sort of fix this, like one called AI Descartes.
Right, Descartes.
Yeah, and Descartes is smart because it takes the formula the AI generates, and it checks its math against existing established scientific theory just to make sure it actually makes sense. But the sources highlight a pretty glaring vulnerability here.
What if the textbook itself is wrong?
Exactly. Does the AI just hit a brick wall if the established science is incomplete?
That is exactly what happens if the data reveals some entirely new phenomenon, but the existing scientific textbook doesn't have the equations to explain it yet. An AI like Descartes just fails. It can't bridge that gap. And this brings us to a fundamental concept in human logic that has been almost entirely missing from artificial intelligence until right now.
Abductive reasoning.
Yes, abductive reasoning.
We hear about deductive reasoning all the time, working from a known premise to a guaranteed conclusion. How does abductive reasoning flip that step?
So abductive reasoning works in reverse. It starts with an observation, a final outcome, and it works backward to find the most plausible explanation for why that outcome exists.
Like a doctor.
Exactly like a doctor diagnosing a patient. The doctor sees the symptoms, the final outcome, and they have to use abductive reasoning to figure out the hidden disease causing those symptoms.
Historically, automating that kind of abductive leap has been an unsolved problem in AI. I mean, it requires synthesizing totally new ideas, not just processing old ones. But that is exactly what this new system, AI Neother, has been built to do. It's named after the brilliant mathematician Emmy Noether, by the way.
A very fitting name.
Yeah. And the way it works is honestly mind-blowing. Our sources break down its process into 3 distinct steps: encode, decompose, and reason. But since it's not just guessing like a normal AI, how's it actually figuring out the missing physics using these 3 steps?
Well, it approaches the problem almost geometrically, like a multidimensional puzzle. Step 1, encode, takes all the known scientific rules and the new unexplained data, and it turns them into complex polynomial equations.
Algebraic geometry.
Right. You can think of these equations as creating intricate shapes or surfaces. Now, if the new data naturally fits with the old rules, its shape perfectly aligns with the existing geometry.
But if there is a gap, if a literal rule of physics is missing, those shapes won't align. There will be a visible, well, mathematical hole in the puzzle.
Precisely, and that leads to step 2, which is decompose. The AI takes that massive, misaligned mathematical structure and fractures it. It breaks the puzzle down into its absolute smallest, irreducible geometric components to isolate the exact, specific space where the unknown variable is hiding.
Which brings us to step 3, reason.
Yes. In the reason step, the system analyzes that isolated gap and mathematically forces the missing puzzle piece to the surface. It does not guess. It calculates the exact geometric shape required to make the entire structure perfectly smooth and logically sound again.
And the paper gives us some incredible real-world examples of this in action. Let's look at Kepler's 3rd law of planetary motion.
This is a great one.
Yeah, so the researchers took AI Neother and fed it all the observational data about how planets orbit, but they deliberately hid the equation for gravitational force. They just wiped gravity from its memory completely.
So the system is looking at the orbits, and it's looking at its incomplete rulebook and realizing there is an unexplainable gap.
Right.
So using those 3 steps, it naturally detected the missing puzzle piece and generated the exact gravitational formula. It derived gravity from scratch just to make the math balance.
Which is wild. But they pushed the system even further with their ultimate test, which was Einstein's theory of special relativity. Specifically the concept of time dilation.
The idea that time moves slower the faster you travel.
Right. For this test, they fed the system the correct time dilation data, but they paired it with incorrect canonical theory. They gave it the old, classical Newtonian assumptions.
Which fundamentally believe that time is absolute and the speed of light can change.
It's exactly.
What's fascinating here is that under those classical assumptions, time dilation creates a massive geometric collision. The math completely breaks down, so AI Neother encoded the system and immediately recognized this huge structural inconsistency.
It essentially rejected Isaac Newton. It stripped out the incorrect Newtonian assumption entirely and autonomously derived the only axiom that could possibly make the universe make sense.
Right.
It spat out an equation that essentially proves the speed of light is an absolute constant.
Yeah.
It mathematically derived the core premise of relativity completely on its own, just by recognizing that the old rules were broken.
And this isn't a one-hit wonder either. Across a battery of major scientific laws, AI Neother successfully recovered the exact missing axioms in 45 out of 47 test cases.
That is a 95.7% success rate at discovering the fundamental laws of nature.
It's unbelievable.
It really is. It's amazing that AI is solving the fundamental laws of gravity, but what's crazy is that we need this exact same physics-first approach just to keep the servers running those very AI models from catching fire. Let's pivot and look at the real-world concrete infrastructure that powers these trillion-parameter models, because that is where this complexity wall is really starting to fracture.
To understand the infrastructure crisis, the sources present a very powerful visual analogy, which is an iceberg.
The iceberg of system failure. So if you're managing a massive data center, the tip of the iceberg, the part visible above the water, is the binary failure. It's the moment the system completely crashes, the link is lost, the dashboard lights up red.
But that red alert is just the final catastrophic symptom. The actual problem is everything happening underwater, which the sources call silent drift.
Silent drift.
Yes. This is the margin decay, the microscopic thermal instability building up in the silicon, the firmware slowly diverging from its optimal state. It is the physical health of the machine degrading quietly over time.
And this leads to what the engineers in these sources call green dashboard syndrome. Your software monitoring tools are looking at the system and reporting status normal. The dashboard is entirely green, but underneath, the physical reality of the hardware is drifting apart.
The crash is mathematically guaranteed long before that red light ever turns on.
And the sources explain why the dashboard lies to you, and it comes down to something called the measurement problem. Imagine you're trying to measure the accuracy of a system clock, but that clock is slowly drifting out of sync.
Right.
If you try to measure that drifting clock using another software clock that is also drifting, you're completely blind to the error.
So if I can jump in, basically you are realizing that we cannot govern a complex physical system using relative software tools. If the foundation is shifting and your measuring stick is shifting along with it, you will perceive everything as perfectly stable right up until the moment of total collapse.
Exactly.
Pure correlation fails at the edge of complexity. Binary red-green monitoring is totally dead. We need an absolute reference, something that does not drift.
Here's where it gets really interesting, because you can't just build a better software clock. You have to anchor the system to something fundamentally unchangeable. You have to anchor it to physics. And that is the core philosophy behind the Extreme Reliability Architecture, or XR. Their entire operational mantra is physics does not negotiate.
Physics does not negotiate. And to execute that philosophy, the XR architecture utilizes what they call a 5-layer ontology stack. It is a rigorous way of mapping raw physical reality all the way up to business decisions, and it starts at the absolute bedrock, layer 0, the physical truth.
And this isn't software reading software. Layer 0 is raw signal acquisition pulled directly from the physics of the silicon itself. But what does that actually look like in practice?
Think of it like taking the vital signs of the machine. It is measuring bandgap reference voltages, which is basically the literal electrical heartbeat of the chip. It's tracking microscopic thermal noise and electron flow.
So going back to our iceberg analogy.
Right. Layer 0 is the sonar pinging the dense ice deep underwater. It doesn't care what the software dashboard says. It only cares about the physical state of the metal.
From there, the data moves up to layer 1, the diagnostic layer. This is where an AI debugger, known as XR RAID, takes those raw physical signals and reconstructs causal vectors.
Causal vectors are essentially the exact domino effect of the physics. Instead of looking for statistical patterns, XR RAID maps the literal physical chain reaction. If component A gets too hot, it increases the electrical resistance in component B, which slows down component C.
It maps the physics of the failure before the failure even happens.
Exactly. Then it moves to layer 2, the semantic layer. This translates that rigid machine truth into human intent. It tells the engineers exactly what the physical drift means for their operations in plain English.
Finally, we reach layers 4 and 5, which are the fleet and economic layers. This is where the system tokenizes reliability.
Tokenizing reliability sounds a bit abstract.
It does.
But think of it like treating the physical health of a server exactly like a financial asset on a balance sheet. The system translates physical stability across a multi-cloud network into actual economic value and settlement.
So if a server is physically drifting, its economic value token decreases in real time,
allowing the business to automatically route workloads to physically healthier machines without humans even intervening.
The real-world impact of this absolute physics-anchored approach is staggering. I mean, let's look at some specific examples here. In the semiconductor industry, in sub-nanometer fabrication, yield drift is an absolute nightmare.
Oh yeah, it's incredibly costly.
This is when a massive batch of incredibly expensive chips mysteriously starts failing quality control. Identifying the root cause used to take these massive manufacturing plants 3 weeks of investigation, sifting through millions of software logs.
3 weeks of a multi-billion-dollar factory standing perfectly still. But with physics-grounded causal AI, that root cause identification was slashed from 3 weeks to just 4 hours.
4 hours. In this specific fab case, the XR system bypassed the software dashboards and looked directly at the laser of physics. It connected a tiny 0.3% drift in a pressure valve, a manometer, to a microscopic shift in electrical resistance much further down the assembly line.
By catching that microscopic physical drift instantly and mapping the causal vector, they prevented $18 million worth of silicon wafers from being scrapped. It is an incredible story of physics saving the day.
And we see the same profound impact in aerospace. They applied this independent hardware-level safety monitoring to aircraft engines. Traditional software would basically just wait for a sensor to trip an alarm.
Right, wait for it to break.
But the XR system tracked the exact vibration signatures of bearings against oil debris data at the physical layer. They mapped the silent drift of the metal itself, giving mechanics 200 hours of advance warning for engine degradation.
Which resulted in 0 unplanned engine removals. 0.
All because they stopped looking at relative software alerts and started listening to the actual physics of the machine.
We even see this in data centers. By implementing this XR system, one fleet saw their unplanned disk failures drop from 30,000 a year down to 6,000.
That's a massive drop.
Why? Because the system isolated degrading data patterns at the physical layer 14 days before the drive actually failed. 14 days of advance warning.
In that same data center environment, they had an issue with latency spikes. 8 major slowdowns a day where the network would just crawl. The XR system traced those spikes directly to background input-output storms, causing buffer saturation at the hardware level.
It mapped the physical cause, and those daily latency spikes dropped from 8 to 0.
Now, underpinning all of this incredible infrastructure management is a very rigorous mathematical framework. It relies heavily on what the sources call the Normalized Stability Index.
This index is what maintains a dynamic stability corridor for the entire system. It constantly perfectly balances 3 physical forces: a generator, a regulator, and a mediator.
Let's ground those 3 forces for everyone listening. What do they actually represent in a physical system?
You can think of it like driving a high-performance car. The generator is the engine, the power and input driving the system. The regulator is the braking and cooling system, the mechanisms keeping the power in check. And the mediator is the transmission, the component handling the actual workload and distributing the force.
So we put a massive load on the transmission. The engine has to work harder, and the cooling system has to spin up to compensate.
Exactly. The Normalized Stability Index calculates the exact interplay of those 3 forces millisecond by millisecond at the physical layer.
At layer 0.
Yes. If the generator spikes, the index mathematically guarantees that the regulator compensates instantly. It ensures the hardware remains within safe operating margins, neutralizing the silent drift before it manifests as an error.
So what does this all mean? Especially for the people writing the checks. Because at the end of the day, physical drift inevitably becomes financial drift.
That is the ultimate P&L challenge. When a massive corporation loses money to operational inefficiencies, 99% of the financial variances they look at on their spreadsheets are just noise. Task forces waste hundreds of hours digging through software logs and financial reports, basically just guessing at the root causes of margin erosion.
But the XR architecture scales all the way up to that layer 5 economic binding. The sources actually cite a massive financial case study. A corporation was suffering a 4% gross margin erosion, which translated to a devastating $150 million impact on their bottom line.
Massive.
Normally, executives would just shrug and blame generic inflation or market forces.
But the XR system anchors economic value directly to physical causality. It traced that massive financial loss directly back to 3 specific physical hardware drivers in their supply chain. It completely eliminated the guesswork and the excuses. It tied the corporate ledger directly to the silicon.
The result of this absolute reliability is unprecedented. We are talking about achieving 99.99% plus uptime across global fleets. A 70% reduction in mean time to resolution, because the engineers no longer have to guess what's wrong. The system tells them exactly what physically broke down to the millimeter.
And an 80% drop in unpredicted hardware failures.
Staggering returns.
If we connect this to the bigger picture, a very clear, profound mandate emerges from these sources. Whether you are automating the discovery of the laws of the universe with AI Neother, or you are managing a 100,000 server data center with the XR architecture, the truth is exactly the same.
Right.
We cannot govern what we do not causally understand. We have to move past the illusion of green dashboard syndrome and anchor our decisions in fundamental reality.
That is the vital paradigm shift you need to take back to your own work, whatever your field or industry is. We have to stop looking at our dashboards and asking, is it broken? Because by the time the light turns red, the physics have already failed.
Right.
It's too late. We have to start asking, is it drifting?
Exactly. Is it drifting?
And I want to leave you with a final, somewhat provocative thought to mull over. We've seen today that AI is now capable of finding the missing laws of physics to explain the universe. We've seen that it can predict the failure of our own massive industrial machines long before they happen, simply by tracking the silent physical drift of the metal. If AI can do that for silicon and gravity, how long until we ask these physics-grounded AI systems to identify the silent drifts and the missing axioms in our own human economic and political systems?
That's quite a thought.
If the math can see a server crash coming weeks in advance, what else is it going to see coming? Think about that. Thank you for joining us on this deep dive.